So, well, Jessica does not need any more introduction, I think. I do want to mention one thing. There's also an Elm of a meetup here in Utrecht. They had one last week, so you have to wait a bit. I think there is going to be a hackathon in a few weeks, so take notes if you are interested in Elm. Jessica is going to talk about the automation part that she showed us in the last talk, in the former talk. And I loved that talk, by the way. Did you? Yeah. It's quite fast for me. I'm quite new to Elm, but yeah, she was like a wizard, eh? Extremely explicit wizard. So, so take it away, I think.
Interested in, oh, there we go. Maybe you're interested in using Rug or writing your own code that modifies code, but also I'm talking about how to write a parser, and we all need to parse things sometimes. Usually it's data that comes in, like even that freaking onEnter event had to be parsed with those Elm JSON decoders. It was a number, and you still have to parse it. So parsing is something we all wind up doing. And in this particular case, I've implemented the Elm parser in Scala using parser combinators. And those are kind of a cool tool that can be a little hard to get started with because the syntax is intimidating. But after this presentation, you will have enough familiarity with it that you won't be afraid, at least if you're a Scala developer, you won't be afraid. And if you're not a Scala developer, you might be even more afraid of Scala. Because there's a lot of magic in them. But the parser combinators, once you've seen a little bit, I was actually astonished for how cryptic the syntax looks. It only took me a few minutes of using it to get comfortable with it. And so by the end of this presentation, you should be sufficiently comfortable with it to be okay, like looking a few things up and being able to write them yourself. And they're powerful tools, so that's helpful. And then as much as people want, I can go into the Rug programs. So yes. Okay, excellent. Look, this is the Rug slide. I will explicitly explain Rug. Okay, Rug is an open source project published by Atomist, which is my company. It was conceived and created originally by our CEO, who's Rod Johnson, which is ironic because Rod Johnson created Spring. And Spring is a Java framework that does AOP. It does bytecode manipulation. It is so freaking magic. It's not even funny. And when I worked in Java, oh, this is being recorded. Okay, when I worked in Java, I was sometimes annoyed by Spring. Because it does things behind the scenes, because I couldn't tell exactly what code was getting executed as a result of an annotation, it was hard to figure that out. You had to be like really familiar with the framework to know what it was going to do. But Rug is completely the opposite. Instead of changing your code after you write it and after it's compiled, but before it runs, Rug changes your code before you write it. I mean, it is, as we've seen in Elm, it does an abstraction at a level outside the code. So Rug is about code that modifies code. Okay, it's about more than that. It's about development automation in general, but the stuff that I'm talking about today is the half of development automation that literally automates development. It literally automates changing code and creating code. But like the little project seed generators, which you could say are creating code, they're a little bit like templates. Really, they're an automated copy, paste, modify. But any code that you let Rug create for you in your project, it's your code. You do what you want with it. It's not like those old style code generators where if you wanted to change the code, you had to change the definition of stuff that generated the code. Did anybody work with any of those? Yeah, and those were a pain in the ass, because they didn't make it clearer how to change the code. But I do like when I have a repetitive task in code, instead of adding layers of abstraction, or like in Ruby, Rails is a good example of it's all convention and there's all this magic behind the scenes that's making you type less, but it doesn't make it clear what's going on. I really like my code like Elm to be super explicit, and Java can be that too, which is nice. Rug works on any language. It is totally not language specific. It is a set of, it's a platform and a set of library things, I guess. We'll see some of them, to make it easier to modify code. Anyway, everything I'm showing today is open source. Rug and the Rug command line is all open source and has been since September, I think. The not open source part like runs it in Slack, so you can like interact with it in Slack, and then that does all other kinds of development automation to interact with GitHub and things like that. So like when I ran, say, upgrade to beginner program and it made changes to my main.elm, I was comfortable with that locally because I'm using Git. I can always roll those changes back if I didn't like them. If I triggered that from Slack, I would have got a pull request. So that's kind of neat, but not necessary if you want to write your own code that modifies code. But behind there, to unpack the transformation, and it's kind of functional in the sense that it's a transformation of data. The code is perceived as data. In order to do like logical, readable, comprehensible transformations on that data, we need to turn it into something structured. And that starts with parsing. And then we can manipulate it and have the framework apply those updates if we want. But it all starts with parsing your code. And I will say that writing a parser for Elm has made me much more familiar with the language. If you think you know your language, try parsing it. Don't try it if it's TypeScript. There's a reason it took Microsoft to create that language. But Java's not bad. Java's not that bad. It's pretty explicit. And Elm is really not that bad, as it turns out. Now, also, some of the other trends in programming today that help with the idea of code that modified code are conventions and frameworks, and we kind of do like our code to look uniform anymore. So Elm format, for instance, my parser, I don't even try to parse un-Elm formatted Elm because that's harder, and there's no reason. Run Elm format. I always run Elm format, so that limits the scope. And it also makes it easier to modify the code because I can count on certain conventions. So that's handy. As parsers go, we are using here a custom parser, and that is the hardest kind of parsing. Let's see how hard it is. Now, to do a little bit of it is actually not hard and kind of fun. So let's pop over to IntelliJ. This part's new. Okay. We need the Scala project. So I have here an outline. Where did it go? Nope. Come on. Oh, man. Sometimes IntelliJ, like, opening is a challenge. Come here. There it is. There we go. Okay. So our objective is to parse a little Elm file. Here's a little Elm file. It's pretty much hello world, except it says parsing is fun. And we can write a parser for this much of Elm, for instance. It's fun to start with something simple and then build it up. And this will illustrate all the different common parser combinators in Scala. So Scala is a handy language for this, and also Rug is written in Scala, so that makes it easier to integrate with the framework. But let's see. Say your objective is to parse this file. When you use parser combinators, you're going to parse the entire file, so that can be a challenge, typically, or at least you're going to parse it from the beginning, not like a regular expression, which you could just find anywhere in the file. So our goal is to read in this file, get its string, and we want to parse it into some sort of syntax tree, some sort of structured data that then we could manipulate if we were to write code that modifies code. And you can use these same tools to parse anything. So what we would want is some sort of Elm parser, and we would want to call a parse method that's pass it the content of the file. Okay, Elm parser does not exist. Create objects, new file. I have imported the Scala Parser Combinators library, extends regex parsers. Come here. No, import it. Okay. And it is a standard Scala lang module. It doesn't automatically come with the language, so it's one separate import, but it is in the Scala lang package. And regex parsers has a bunch of magic inside. I'm going to try to avoid digging down into that class because it's a little scary. But when we extend it, we become a parser, and we can create this parse method, for instance. We want to parse some input, which is a string. Get out of my way. And we want to output, well, what are we going to output? Some sort of tree. I'm going to have a tree, which is a syntax node. And we're going to do that by calling parseAll, which is a method inside regex parsers, and we'll give it the input. And parseAll says, I need my parser to match the whole file. Oh, and I need to give it a parser. We will create a parser and call it Elm module. And then we will react to the output of that. Alt enter. Okay, it doesn't like me. It wants an equal sign. Okay, Scala just, not Typescript. They're just enough alike. The syntax is just enough alike that it's really painful switching back and forth. Okay, so we get either success. When you parse something with these parser combinator libraries, you get back either success or no success, which in fact can be an error, which is it threw an exception, something was really wrong, or it can just be a failure. I didn't match it, maybe somebody else will. And in both these cases, I'm just going to throw an exception. No, I better put the failure in there, because if I put boo, then it's definitely going to happen, and I'm not going to be able to. Cannot resolve constructor. ToString. Okay, come on, Scala. All right, so there, but if we get success, we get the result, and you don't have to worry about the next. That describes any input that's remaining. Okay, let's paste in a syntax node. A syntax node, I am using nice abstract things. It's a tree node, it's got a name, it might have children, and it might have a value. In this case, I'm going to provide a value to a leaf node, but not to the parent. It's convenient to have these be the same type. We'll see that later. Okay, so now it's time to create our first parser. Parser combinators describes, there's like two components. You can have a parser, which knows how to process a piece of text and either match and output some like useful object like a syntax node, or you can have a combinator, which is a function that either takes a parser and transforms it into a different parser, or takes multiple parsers and combines them into one parser. That's the combinator portion. And in this little example here, we will create several parsers. We will use about 6 combinators, and we will create one combinator, one custom combinator. All right. Which in the course of which we will create a custom parser. But right now we want an Elm module. Okay, first thing to watch out for in Scala Parser combinators, use def, not val, because they are stateful. So in Scala, def says it's a function, and val says it's a value. There's only one of it. In this case, it's a function with no arguments, but every time we call it, we will get a new one. And let's start with, I don't know, what's the easiest thing? Match everything. .star.r means make a regex out of that string. Okay, and there is implicit magic, implicit conversions inside the regex parsers that can convert a regex into a parser of a string. But we want a parser of a syntax node. So here's your first combinator. Caret, caret. Obviously. This, you know, I generally hate Scala's infix symbol functions. But bear with me, it actually, I don't hate all of them now. And these ones are actually okay because they're entirely local. Those implicit conversions only exist in this class. See, can you see like the really light underline here? That's IntelliJ for magic. Something magical is happening here. In this case, yeah, see public def caret caret u. Yeah, so the u is taking a function of string to u. U is the type parameter here, so that's going to be a syntax node. So it's going to get a function of string to syntax node, and it's defined on parser, and it's going to give us another parser. So I can take in this string, which is everything, because it's star, and give back a syntax node. Syntax node.leaf, and we'll call it everything else. Great. And what's its value? Everything. There we go. Oops. Now, I very cleverly, here's another Scala trick. How many people are Scala? About half, maybe a little over half. Okay, good. So those of you who are Scala will, maybe you actually like this magic, and those of you who are not can be amazed. For instance, I very cleverly implemented syntaxNode.leaf with 2 parameter lists, which is so instead of, here's an anonymous function, I didn't need the case there. Instead of passing a whole anonymous function to this caret caret combinator, I can just pass syntaxNode.leaf and it will magically go in. Okay, because it's curried there. All right, so here's our first parser. It parses everything. Let's see what that does. Let's go over here and run this parser play app and see what the output is. It should just read in the whole file. And benefit of parser combinators, this is one of those tools that you can feel like a wizard when you know it really well and you know how they all fit together. And coming back to it can be painful. Okay, and it is one of those tools that's, you know, they did put some effort into the error messages. They could be a lot worse, but they are not pretty. Exception, failure, end of input expected. So it found import and it was looking for end of input. And I kind of get this error on purpose so that when you get it, you will know what to do, which is dot star doesn't match new line. So in the brilliance of regular expressions, we will say dot anything or new line. And that's going to work. So there's all the subtleties of regex and a few more. Okay, great. This time, how big is that? All right. This time we've got syntax node. Can you read that? Yeah, it's not very exciting. It's not the most exciting reading anyway. Syntax node of everything else, no children, and it has a value, which is the text we parsed. Great. Now we can start combinating and building up. And this is the fun part where you get to do just a little bit at a time. So this is going to be our everything else parser. We'll just leave it there. And Elm module is going to be, let's see, it's the word module. And then we're going to have like the name of the module. So here is our second combinator. It is the concatenation combinator of, look, these 2 tokens happen one after the other. This is a string literal, which is going to undergo a magical implicit conversion into a parser that only matches exactly that string, except that there's more magic than that because it will happily drop whitespace on either side. By default, you can change that in regex parsers, but by default it'll drop whitespace and match exactly that string and then skip over whitespace. And then we're going to look for, I'm going to make a function for this, an uppercase identifier, which we want to call module name. And that uppercase identifier is going to be pasted. It is a parser of SyntaxNode, and this is why I pasted it, because you don't want me to type that regular expression. An uppercase letter followed by some more letters or numbers or underscores, maybe. And that gets put in a leaf with the name that is passed in, so that's going to be a module name. Okay, so now what we have here is, are you going to give me the type? Yes, it's an expression of type parser tilde bunch of things. The secret here is to convert that into a syntax node. And now that tilde gets used again. So we have the word module followed by the module name. And in this case, I'm using a case expression to deconstruct with the pattern match, deconstruct the thing that was concatenated together into its components parts. And it's going to get happy when I say SyntaxNode.parent module, and we'll pass it those two things, except I don't actually care about this word. Okay, so now it's happy. I use the tilde here to say concatenate these things, and then in the case statement, I break them apart, and this will always match, and it will be happy. Except I don't actually want the word module. I don't care about that. So here's your next combinator. I don't care about that combinator, which is very similar to concatenation, except it says the stuff that the arrow is pointing to, I care about that. The stuff on the other side of the arrow, just drop it. And then I don't have to have module here. I can just match the module name. And then we can see if that works. So now we're pulling out our first piece of structure, our first piece of interesting information. Well, we would be if it worked. Information. End of input expected. It really didn't like expose. Oh, I forgot to add everything else, didn't I? We still need everything else because it wants to parse to the end. So here we have module name and we have the rest, and we can add that in here. Okay, so now we should get a parent node with 2. It's going to have a module name and the rest, and indeed we do, way down here in this giant thing. And so the thing is, like, one-dimensional prints with trees are really crappy. And it happens that I've hit this problem before, like in a totally different like Scala thing that I was writing. I was dealing with some sort of tree, and I'm like, I need to print the tree. And I went to, I was like, oh, Rug CLI has some code that prints some trees. So I went and I dug that code out, and I found it, and I put it in my project, and I made it a little more generic. And then the third time I needed to do that, I made a program for it. In fact, since then, I have made a program to make a program for it. So first I will run the program that is the output. I don't need this anymore. In our Scala project, I want to bring in the tree node printer. So tree node printer, I'm calling this a libit. It is something that is, oh, you're going to yip at me because I haven't made a commit. Okay. Because I'm asking Rug with a -R, I'm like, make a commit for me with this edit. And it'll yip at me if my git status is dirty. Okay, so I'm calling this conceptually a libit. It's a little piece of code that I want in many places, or even just a couple. And the traditional way of dealing with this is to pull out a utility library. So you pull out a utility library, and pretty soon everybody in the company is dumping stuff into that utility library. Whenever you want to change something, you have to upgrade to the utility library, and everything breaks because everybody's making these stupid little changes to the stupid utility library with all these functions that have nothing to do with each other. So part of my personal mission at Atomist is to kill the internal utility library. I mean, sometimes you need an internal library when there is a business reason for that code to be the same in multiple places. And that dependency is an entanglement, and it's a communicative, necessary entanglement that is expressing a business-dependent, sameness, I don't know, abstraction. Yeah, there's a business abstraction in that. Great, use those libraries and upgrade them, and I have automation for that too. But the utility library where it's just a matter of convenience, of I don't want to cut and paste this code, I just want to have it at my fingertips, whoever writes that in that utility library first and then imposes it on everyone else in the company, no, okay, if you want the convenience of having the code in multiple places, let's just make it really convenient to cut and paste. And that's what I'm doing with this little libit thing of over in my, where'd it come from, Jessica Parser library somewhere. That one happens to also be a parser that I exported it from. I made my tree printer class very simple, and it's just this function, and I made some tests for it. Question? They can add stupid little functions to the libit, but once I've copied it, I will never get those changes. That's okay. So that's an interesting question. So actually, I don't have this implemented yet, but we're actively working on. We call them features because they're more general than libits. Libits are a special easy case of this. Code that will notice when you okay. So step one, I identify this class that I think I might need somewhere else. And then I run a program, it's a rug, of course. I run a rug that says, okay, I see your class that you just told me you want to export, and I'm gonna go find its tests, because I recognize Maven project structure and also my TypeScript project structure, and it says, okay, I'm gonna grab it in its tests, and then I'm gonna create a program that will copy those files into another project of your choice. And that program is also a rug. So here I have a rug for making a rug, which is fun. And that's fine. And now I'm running that rug, that output rug, because that output rug says, okay, I know how to copy these files in. So I published the tree parser libit rug here, which knows how to copy whatever version of those files existed in that project when this rug was since I'm running it locally, installed on my system, or published up into the rug package management thingy. And this one is going to be like, okay, I know how to copy those. You give me a package name that you want them in, or Dina, and I can put them in. I like to put them. I could say util here, but I'm going to call it libit because it's a little distinctive. Okay, and there it goes. It copied in those two files. When you declare a dependency on something and you can't get any updates without getting all of them. It's like I've forged a permanent relationship with that code. But here, I haven't married the code. I've adopted it. It's mine. I can do what I want. So I can and will modify my tree printer, and it won't affect anyone else. Now, if I actually wanted to follow the tree printer feature or libit from the whatever source I got it from, that is an automation feature that we're working on now, such that whenever there's a change to that, a commit that changes that, I get a pull request. Not a dependency upgrade, a pull request. So I can see the change and I can decide whether I want it or not. And I can be like, oh yeah, sure, merge that. Or I can be like, nope. Or I can be like, unfollow. Your updates are not the same motivation as my updates. So this is, I don't know, I'm really excited about this, obviously. I've actually wanted this kind of thing for like a couple years, just to have this kind of automated sharing of code without marrying of code. I don't want, it's not like essential business logic that tree printing is the same in two places. And if I need it to work on Windows over here and Mac over here, I don't have to make it more general. I can just customize it as needed in different places. Okay, so I didn't plan to go ranting on libits for like 5 minutes, but clearly I'm pretty enthusiastic about them. But now I have some code. And it should have made a commit. Yes, it did. Code. Now I should be able to use tree printer to print that tree, and it'll look all nice and stuff. Tree printer, bring it in. I want to draw the syntax node of the parse tree, which it doesn't have draw syntax node. It just has a generic draw function for trees in general. Draw syntax node. So I have to tell it, okay, for a syntax node, how do you get its children, and how do you want me to print it? You know, what's its toString? And given those two things, the tree printer blah blah utility code will do the tree bits. And let's run that, and we should get a better output, something we can work with. Yay! Whoops. Make this bigger. No, this one. Make this one bigger. There it is. Okay, so now we can see we get an Elm module, and it has two children. It has a module name, which is main, and it has everything else, which is everything else. Moving on with our parser combinators. Right, we have main up here. Before we get to everything else, we actually want to say, we want to get those exposings out. So the next thing in everything else, would you show me everything else, please? Is exposing main. So the next thing we want to pull out is this exposing word and then main. And like conceptually, I can see that I'm going to be able to use the same parser for this as for this. So I'm going to make it another parser so I can reuse it again in the imports. So I'll make an exposings parser, and exposings, that will be a parser of SyntaxNode, and it will be the word exposings followed by parentheses, and I separate those so that it'll like drop whitespace between them. And then I don't care about those things, so let's point this direction and say I want the exposed thing, and then after the exposed thing I can use the other arrow to say I don't care about this parenthesis, just this one thing right here. And then exposed thing, we'll put that in a function which we'll wrap it up. Okay, thing, SyntaxNode parent, this is going to be an exposings, and it's going to have that one child of the thing, which I have not named very well. And then we can define the exposed thing parser. And that was, let's see, what does it say? It says main, so that's a lowercase identifier. And we'll call it exposed function, because that's what it is. So here I'm giving like information to my structure there. And lowercase identifier looks a lot like uppercase identifier, except it starts with a lowercase letter. In my real Elm parser, these identifier parsers also take into account keywords, and they won't match keywords, which is really useful. But for what we're parsing today, we're not going to need that. And there's some anger. Oh, because I added the exposings there, but I didn't add it here. I do like the compiler most days. All right. Oh, there's still anger. Exposings expected, but E found. Really? Seriously? Thank you. See, have y'all ever done mob programming? You can see why it's great. Okay, I wanted it there, and I didn't want it here, yeah. There we go. Thanks. Awesome. Now we have exposings with an exposed function of main. We've got that much. Well, let's do the imports. Actually, let's make the imports a little harder, because realistically, here I'm importing free things from HTML, but let's also say we imported mouse. We're not going to use it. The exposings is optional on imports, and we can have more than one import. And we need to introduce repetition and optional combinators. So when we add the imports to the Elm module, we'll put them right here. And we'll start with just one import statement. And we'll make a parser for that. Nope, not inside there. That's not a place. We'll make our import statement be a parser of SyntaxNode. And it will say the word import, which we don't care about, followed by the, let's see, there's a uppercase identifier, which is the imported module. And then there is optionally an exposings, right? And then we'll have to caret that, and we're not going to get the import, but we're going to get the module, and we're going to get the exposings, and we can put those into a parent called import statement, and with those two children. But exposings, I used opt here to say it's optional. So this is opt is a combinator that takes a parser and creates another parser that will match something if it's there, but if not, it won't fail. It'll just return nothing. Or it's nothing in element Scala, it's called none. So we'll get none. So exposings here, we might actually get some exposings, in which case we need the mod. critique of module and exposings. Didn't I call it module? Oh, that's a tilde. Or we could have none. We can use this. So this is pattern matching in Scala. This syntax is technically a partial function that it'll throw an exception if it can't decompose its input into one of these patterns, but it always will. And if we don't get import exposings, great. We just have a module that's imported. Let's see what we get when we match that. We get some anger. I forgot this again. Imports is now belongs here. Imports. I'm just going to call it imports, and we'll stick it in here. There. So everything that we parse, we have to like fit it into the structure, and we've done that. And what do we get? And is this? Oh, come on, be big. There we go. We got main, we got exposed function main, we got import module HTML, and we did not match the exposings, dun dun dun. And that's because two reasons. One, there's 3 in here, and there was only 1 up here. So our exposings can actually be, we can have multiple ones, multiple exposed things. And if I do rep, so rep says 0 or more of something. So that's a combinator for 0 or more, and it will actually give me a sequence. So now thing, this is angry because thing is already a sequence. Brilliant naming, Jess. Rod would not be happy with you. And right, so now we're getting a sequence back, but ours is comma delimited, so we use rep sep. And rep sep says 0 or more of this thing delimited by something that matches this parser, and it converts the comma into a parser. But in fact, we always need at least one of those, so I should use rep 1 sep, which says at least one of something that matches this parser delimited by this parser. And it'll throw the commas away, and I'll just get the exposed things. And it's still not going to match because there's one more crucial combinator, and that is that HTML doesn't match. Now see, I'm not helping much here, am I? If I wanted to see why this doesn't match, right now it's perfectly happy to just dump all that stuff in main, or in everything else. If I go change everything else to say, the next thing I should get after this stuff is main, okay? So now it's not going to match that and it's going to give me a better error. So this is one way that I manipulate its error messages, and now it says it doesn't like this capital H. Expected string matching lowercase identifier, but H found. And I know how to deal with that. In fact, an exposed thing can be either a lowercase identifier of an exposed function, or I'm going to have to put the or thing up there, aren't I? So or is a combinator. Pipe here is the or combinator. It could be an uppercase identifier, in which case it's an exposed type. And then we might get farther. And we get down to import mouse, and that, it's looking for an I, and I wanted it to be able to get all the import statements, but it's not. So here we use our rep combinator again, and this becomes a sequence of import statements, which makes this angry. And I have to like do sequence concatenation instead. That's no big deal. Plus plus seek. All right. So now we've constructed our sequence of children from various elements and a sequence of elements. Okay. Now we have our tree. Let's see it. Let's look at this. There we go. So we have 2 import statement children, and they have imported modules, and one of them has an exposing. And you can start to see how we can break the code down into something we can manipulate. So like in my add import program for Elm, I take a look at this and I navigate down the tree, and I'll show you in a minute, but I do that with XPath. I navigate down into the syntax tree to find the import statements, and I look for one where the imported module matches the one that I requested to be imported, and if it's not there, then I know I need to add it. So I take all those import nodes and I sort them, and I find the alphabetical place to stick it in, and I stick it in. And in order to stick it in, I have to be able to update the file, which means I'm going to need to know where these nodes are, which we're going to do in a minute, right after I magically paste in the parser for the rest of this little program. Because we've seen all the important combinators. We've got OR, we've got more than one, we've got at least one, we've got delimited list, and we've got concatenation, and we've got concatenation with I don't care, and we've got the little caret, which is basically map. No, it's literally map, to transform the output of one parser into a different output. And that's really what you need to know to write Scala Parser combinators. So yes, they're cryptic, but there's only a few of them really. Right, so let's just paste in the rest of the functions. P for parser combinators, parse function. Nope, this one. All right, so now I have this function declaration parser, which is what I want to add. So we can have exposings, we have the module name, exposings, imports, and instead of the rest, we will have a rep, because you can have lots of function declarations of, I put this in a little sub-object, so it's function.function declaration. Why are you angry at rep? Because I put that in totally the wrong place. Yeah, this is going to be functions, but I'm going to replace everything else with the function declaration, which we can hypothetically have more than one of, and we will add them to here. Let's make sure this actually parses. And then the function declaration here, okay, it worked. Here is our full tree. Come on, be a little bigger. There we go. So we got a function declaration. It has a name of main. It has a type of HTML with a type parameter of never. So one beauty of writing your own parser is that, oh, it's in your head. You understand it. And I think this is just like brilliantly and obviously structured because I created it that way. Totally. So, but you get to name it something that makes sense to you, which is really nice. And so I have a function application with a called function and some arguments. We can look at the parser for that a little bit because it's a little more complicated than the others. A function declaration, be less big please, is an optional type declaration followed by a lowercase identifier, which is the function name, and then the equal sign, and then an expression, which we shall call body. And the expression itself is this thing. It's a function application or a list literal or a string literal. Now, in real life, in my Elm parser that I use for my my Elm rugs, that list is like 8 things long. There's records, and there's records with a such that, and there's numbers are a thing, and there's like qualified function names, and there's constructors. Anyway, there's a little set of expressions, but this is where you really kind of get to know your language when you write a parser for it, because great, and it's fun to express optional type declaration. Okay, and that's also fun when you're just parsing data that's incoming, because you can use like your business's universal language to describe your parser, and hypothetically make a parser that is expressive of what the data should look like, unlike a regular expression. Okay, so we have this expression and these ors, and these order is important. Watch out for that. The first one of these that matches is going to match. So be careful with that, and make them like increasingly specific. Now that we have this parser, I would like to use it to update some code. But in order to update some code, like I said a minute ago, I need position information. Because one of the things that Rug does that most parsing libraries don't is provide direct update ability. Provides you the ability to not only dig into the structure of the code and find out what's there, but to change it. So it can track a set of changes that you've made, and then on request, apply those to your actual file system. In order to do that, I need that position information. And in fact, that position information is actually available to a parser. Just by default, I can't get at it. So if I make a custom parser, I can get access to that position information. So that's the next thing to do. First, we'll need something to parse. So instead of a syntax node, let's have a positioned syntax node that knows where it is. And the position syntax node is a lot like the syntax node, but it has start offset and end offset. And to get one of those, I am going to need, a custom combinator. So let's make, instead of having to like change all of my parsers to special parsers that can have the position, I'm just going to make a function that accepts a parser of syntax node, the thing we already have, and it returns a parser of position syntax node. So that's a combinator. It takes one parser and transforms it into another. And we will do that by, in our combinator, creating a parser of syntax node. And IntelliJ will say, you need to implement the method. And I will say, thank you, that is what I want to do. So the apply method here, let's see, we have, is going to accept input. This is the method at the core of Scala Parser. And it accepts this input object, which has, oh, I knew I shouldn't have gone in there. Don't go in there, Jess. Trust me, it has position information, and it has like the string that we're trying to parse. And I want a parse result. Okay, so to get my parse result, I am going to call my inner parser and give it the input, and then match that, and it's either going to succeed, in which case I can create myself a position syntax node, or it's going to fail, in which case I can just pass that failure on. Right, so this result here is going to be a syntax node, and I need to turn that into a position syntax node. So here's a position syntax node. It has result.name, result.children. We'll copy the children, and we'll copy the value option, and we'll add the start offset, which I need to get, and the end offset. So now I'm going to use this next thing, which this next is going to become the in to another parser. These are the same type. So it has offset. So that's going to be the end offset after my syntax node has my syntax node parser has matched. That offset is in there, and before that syntax node has matched, it's going to be in in.offset. Bow, and that's the start offset, Jess. Except I just happen to know that I need to call handle whitespace in order to skip the whitespace, and that wants the in.source. Okay, so this is a superclass method that is going to skip the whitespace up to the next stuff to make it match. And this is fine, so I get the start offset of the next token, and then I do the match, and then this is angry because the child nodes here are in fact syntax nodes and not position syntax nodes, so let's just change that. You now have children of position syntax nodes, which is going to make a lot of things very angry. Yeah, including this one. In the end, oh, I forgot to wrap this in success. This is, I need to pass on the success, and I need to pass on the next, because this is the one part that should be happy. But our parse method, which is now going to return a position syntax node, is all unhappy because all of our parsers are giving us back syntax nodes. All of them. There's dozens now. I pasted in a couple. So what we really want is for our Elm module to be a parser of position syntax node, and we want position node here around all of our parsers. All of them. So we have to like wrap them all up in that combinator, and then they'll all like very cleverly hook in and grab their positions and put them in there. But I don't like making that change. So guess what I did? I made a rug. And I'll get this running, and then we'll go look at it because it's kind of interesting. Where's my wrap function? Here it is. Yeah, so this is a local rug that I made just in this project because I only expect it to be useful in this project. I mean, I guess it could be useful in like other Scala Parser combinators that I write for the same purpose. But right now I only need it here. So it's right here. Wrap function. What did I call that? Wrap position node. Type, Jess. Type. There it is. Okay. So here's a rug. It's a TypeScript class that implements edit. And so it has an edit function that gets a project, which is an in-memory representation of all the files in this repository, this directory. And I get this path expression engine. And here I'm using another language extension. We're currently creating one to parse Elm files. This Scala file one parses Scala files using some open source Scala parser, I believe. We did not write our own. Thank goodness. And so this is XPath approximately, and it says navigate down into the project into these directories, or these children nodes, which happen to be directories, and then find all the file nodes. The double slash means descend as far as you need to find a file node such that the braces are a test. The name of the file is elmparser.scala, and then in there, this call to Scala file says a little more. It doesn't just navigate down into a child node. It processes the file as a Scala file node, which means it runs it through the Scala parser. And then we descend anywhere, and now I'm using somebody else's, which you see how my Elm names were quite beautiful and lovely, and other people's names are really cryptic. What is a def and def? I don't know, but I made a rug and ran a program to find the path down into the piece of the file that I wanted, and by like position, and so it can do that, and then it gave me a big long path which included more stuff, and I was like, I don't care about this. I'm pretty sure def and def means def. And type apply, I don't know what's with the apply bit, but I do want to know the type of the def, and it's returning a parser syntax node. So anytime you get a def and def with a child node, name type apply with a value of parser syntax node, give it to me. I want that def and def node. And then, so I say with each of those, is like a for each over those nodes. Then I get the value of the whole thing. And I just printed out. That's not very exciting. I take that type apply node and I update it to parser position syntax node. And this actually changes the file in memory, not in disk yet. It only does these changes to disk if everything succeeds. And then I get its child node, which is term apply infix, which is the secret Scala syntax tree for, it just happens, see, they weren't nice. They didn't wrap the body in a parent node called body, no matter what it is. It just happens that all of the functions that I want to update happen to be infix function calls, because they all use either tilde or caret caret. And when you're writing automation for your own work, if it works, it works. Who cares why it works? It's yours, and if you need it to work a different way, you'll make it work a different way. So in this case, all right, I'm just going to update the body of that node to whatever it was before with position node in front of it. And then I do some more printing, which is probably going to print a lot of stuff to the screen. Yeah, it printed a lot of stuff to the screen. Okay, so it updated all of these. And you can see how many updates it did. Wow, that was a lot. I'm glad I didn't have to do those by hand. I probably could also have done them with the search for place in my IDE. But yeah, I mean, pick one of your tools and know it that well. In my case, I already knew rug, so there it is. Yes? That is a really good question. So the question was, do you do something special in your parser to handle comments? And in my Elm parser, yes, I do. And specifically, like when you get like the parsers that people have written, like because they're trying to do code, static code analysis or something, they ignore comments. And they will just skip over comments. In fact, they'll just, in a separate phase, take out the comments. But when I write Elm code, I care about those comments. Like -- view in Elm has a semantic meaning, not to the computer, but to people. So the comments become very important. So yes, in my parsers, I'm very specific to include comments as a part of the syntax tree. In Elm, you can have like nested comments, and there's documentation comments. There's like, you'll get errors if you try to publish if you haven't documented all your public methods. So these comments they're not throwaway. The Whitespace is not throwaway. This stuff is meaningful to humans. And when you're writing code to change code, you can make that code meaningful to humans, not just the computer. Fortunately, in our hello world for Elm, we didn't have any comments, so I didn't have to mess with it. But yeah, in real life, that's totally a thing. And I don't think I handle absolutely everyone yet in my Elm parser, but I need to. Some of them are tricky, like the till end of line one. Okay, so this probably worked. This probably changed our Elm parser, and we have, things are still angry. It did say positioned node, blah, 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 blah. Oh, that's because I forgot to tell this one that it now takes position syntax nodes as children. Okay, so now almost everything is happy. There should be one error, which it hasn't noticed yet. Oh, okay, I'm good. Usually when I run this demo, I give exposed thing a type of parser syntax node, and then it wraps position node around this, which it doesn't need because it's just an OR of two position syntax nodes. And so I missed my opportunity to make the point that it's okay that this editor isn't perfect. So I ran it and I had to change one place manually. That beats the heck out of changing this many places manually. Yeah, so that's a fun one. Right, so we made the position node. We should be getting position syntax nodes. We should be able to run these and see the positions, but I need to replace this in tree printer with one that does position syntax nodes, which is number 12 down here. Yes, import the thing. Yes, do it. And we should be able to see position syntax nodes in our happy tree. And then once we have those, then I can integrate this. This becomes a custom language extension. So I said Rug was language neutral, and for every language you can always do straight file manipulations, just that one-dimensional, your code is data because it's ASCII. But then when I want specific custom stuff for an individual language, I can write a parser. I can actually do much more lightweight stuff than write a parser, but hey, somebody asked to see Scala Parser combinators, and they are kind of cool. And it's useful. Okay, so let's see, parser plate. Did you actually run? Are you still thinking? Please to run the editor. All files are up to date. Yeah, so great. It's probably, oh, here it is. Yeah, it's hiding down here. Okay, so now you can see that we have more than just the value. We have now acquired all the offset information, and that's what we can use to actually change these things within the file and do more than just look at them, because all that white space is meaningful, and when I edit my code, I don't want to reformat it all, typically. In Elm, I don't care. I could just Elm format, but in other programs, I really do. That white space is meaningful to a person. Okay, in order to make this a Rug language extension and like run a program with it, yeah, I make this file. Where does it go? Elm language extension .scala. So other than the parser, adding an extension to Rug is not too bad. I make this much code. I say it's named Elm. That's going to show up in the path expression, and it matches any file that ends with Elm. And then I can convert a file to a syntax node. Actually, it's an option of a parse node. So sum of whatever Elm parser returns f.content. And that's going to be angry because it's not quite a parsed node yet. So this is a Rug class. And come on, be angry. Yeah, it's angry down there. All I have to do is say, hey, position syntax node. You extend parse node, and that should extends with an S. Just import it. I don't want to create it. Okay, poof. Because I happened to create parse node, and I created this interface, in fact, for this presentation and put it in Rug. it just magically works. But this actually is not painful. It's a node with a name and some children and a start offset and an end offset. It doesn't even require the value because in order to be able to update the file, I don't need to know the values. I'm going to have that separately. I'm going to have the file content. I need to know the names and the structure that you have assigned to the positions within the file. That's the structure that is returned here. And once I have an Elm language extension, and this is all happy, then I can test it. Elm language extension test. Okay, so this is a Scala test that says read a project from source test resources, that's where main.elm is, and apply this path expression. Evaluate this path expression on that project. And the path expression says, look at main.elm, parse it as an Elm, which is going to use our parser. And then look for a function declaration such that the function name has the value main, and it contains somewhere inside it a string literal. That string literal was, if you'll recall, parsing is fun. But in our test, we are going to find that, make sure we found exactly one string literal inside main, and then we'll change it to hello from Utrecht. And then we will print the content of that file. This is running in memory. It's just a unit test, so it's not going to change the file system. For that, I have to make a Typescript program. And yay, it's green. So it did. It changed it to something that says hello from Utrecht. And that's the updating portion. And then, if I want, I can, to see whether it actually works with like actual rug command locally, so that you could, I mean, if you have like a particular thing that you wanted to write a parser for and run rug on, I need to Maven install it locally, and inside my little rugs, I've got a dependency declared on that, and then I can run change main to print. So I've got a rug in here called change main to print, change main to print. Maybe not. Search everywhere. Change main. Maybe it's not in here. Maybe I put it somewhere else. No, it's totally in here because I can see it right here. IntelliJ does not want to reveal it to me. I can open it in VS Code. Editors, change, okay, maybe I don't know where I put it. Update, thank you. I named the file something different. That was not brilliant. In fact, I am completely wrong. I named this thing update main string. And I don't even know what editor I'm running. Yeah, well, no wonder you're happy. Okay, it is update main string. And it failed because, oh, -L. I need a -L. This is a local editor, and I have not like run rug install to push it up to a Maven repo on my system. But it's in my current repository, my current project, so I can say just run it anyway. And we will see, okay, so this actually updated on the file system, and then we can see main.elm. Hooray, it works. Okay, there. So that is from 0 to a parser that integrates with rug, but really, I don't write these parsers very often. I did it for Elm because there's no antler grammar, and I wanted to give this presentation, and I wanted to really understand my Elm program, and I wanted to be able to break it down, because on top of that parser, if you noticed earlier in my Elm editor, I didn't list those path expressions. I said, I had a different object that I said .add import. So I've like encapsulated the structure of the Elm program in TypeScript, and I can express that an Elm program, basically I'm expressing the Elm architecture in a TypeScript program on top of a parser that expresses the Elm syntax. So I can say things like, get me the messages, get me the model. So that's why I have a custom parser for Elm. Now, the parser that we saw today was about 100 lines. The real one that parses Elm formatted Elm, and it can do almost everything in my Elm stuff directory, which has some really obscure stuff in it since it's like the language itself. So it's pretty effective at parsing Elm. It's 500 lines and a little more complicated. There's a couple things I wanted to show you in there just because Elm regs, where is Cat's parser? As like watch out for these when you're doing Scala Parser combinators. What have you done with it, IntelliJ? Okay, so here's like the list of Elm expressions. There's position node. What is that? Oh, here's an optional comment. So here I'm looking for comments, and I'm trying to like group them in the tree with the things that they're about so that you can update those together. It could be a field access, it could be a function application, and then there's some of these that are nicer than others. And at the very end of this list of things, so when it gives you an error, it tells you that it was expecting whatever was last. It was like, I'm looking, so if it is unable to match an uppercase or a lowercase identifier, it'll say, I was looking for a lowercase identifier. Where is my lowercase letter? When really, it was looking for any whole list of things. So this is something super clever that I came up with. So at the very end of one of these big ORs, I give it this like hint parser, and here's a custom parser that matches, it looks for exactly what I tell it, so it'll look for an Elm expression, but if it actually finds it, it'll throw an exception. The point being that when none of the things in this list match, it will say, I was looking for an Elm expression, which is a lot more communicative. So even while you're writing your parser, you can think about the error messages. And since this is an Elm parser, and it's about Elm, it cares about the error messages. It wants to be communicative. So that's kind of clever, and I should blog that. But the point being, custom parsers are hard, and they're a lot of work. It took me 2 or 3 days to write that Elm parser, and I fixed some bugs in it since then. And that was the second time I've written an Elm parser. So it would have been longer the first time. And so if you are thinking about writing a parser for your language for fun, go for it. Because you'll learn a lot about your language and it'll be entertaining. But if you're thinking about doing it for work, as a yak shave for something else, I do not recommend it because it won't be worth it. It's a lot of work. Instead, how about a nice ANTLR grammar? So ANTLR is like this standard for parse trees. It's a standard for expressing the grammar of a language. So it looks like this thing, which, yeah, it's about that. I don't understand that, so I made it really small so that you wouldn't understand it either. But this file is actually, I think it was like 1,000 lines long, and this is the Java ANTLR grammar. However, if you have a Java ANTLR grammar and you want to use it to make a syntax tree and navigate it with XPath expressions to update pieces of Java, this is the entirety of the Scala code you need. So it's just that class and the file in a Maven repo. So you give it the ANTLR grammar file, and basically a parser is created for you, a parser that finds all the position information and lets you update. And so then you can navigate in the tree according to the ANTLR grammar. And you can run a program to find the ANTLR grammar for the particular thing that you're interested in. Yeah, so that's way easier. So I would much sooner use an ANTLR grammar. Elm does not have an ANTLR grammar, so I didn't have that option. On the other side, you can change any sort of file just as a file, and regular expressions are really powerful. So a lot of my rugs that I write is, and I mean, I could have implemented them as bash scripts, so if you don't want to learn rug, I mean, so you can still automate your own work. Just use a bash script with regular expressions, and please don't ask me to modify it. Because in fact, I implemented that in a rug with a regular expression, and the regular expression looks like that. And as regular expressions go, this one's pretty clear. It has like words in it, like main and text. So I can say, and I have in the past, and I frequently do, I don't need a whole parser to do a straightforward manipulation like this. I can just use a regular expression, and then I can do that wherever. So automating copy, paste, modify is totally a thing. And then the negative of regular expressions is how cryptic they are. They're basically Perl. They're half of Perl. I mean, half of what I do in Perl when I wrote Perl was regular expressions. So they're super useful for parsing, and they're super fast to write if you know them, but really, really, really hard to debug and hard to understand when you come at them later, which, since I'm a fan of Elm, it's because I can understand it when I come at it later. So there's this thing in between, and this was open sourced by Atomist Tuesday, and I'm pretty excited about it. It's called microgrammars. Also, Rod came up with this one too, based on a paper. Microgrammars, like regular expressions, match just a piece of the file. So you can search through the file for something that matches it. And they're less cryptic than ANTLR grammars, and they're way less cryptic than regular expressions. And the idea being, I just want to say, look, I want something that looks kind of like this, and it has these parts, and then let me update the parts. Because in regular expressions, part of what made this Part of what made this complicated is the group capture. The outer parents are a group capture, and the inner are not. Can you tell? And then when I do that, I have to say like $1 in the replacement. Here's the microgrammar for that, and we're still working on the syntax. It's going to be better, but the idea being I can give it a string, and that string looks like what I'm trying to match. So it says main equals, and then I've got this little call out of the before text because I need to save that piece potentially. Text, quote, stuff, and then currently I have to say, I have to define the grammars for those inner bits, which are, before text I want everything until the text, and in the content I want everything until the quote. Personally, I'm working on making that look like this, so that the default of any variable that you define will be until the next token. Basically anything .star but not greedy, so that it will do its best to match main equals something text content in quotes anywhere inside the file. And then unlike a custom parser or an ANTLR grammar, we don't have to understand the whole file, because this is what we do when we look at code. We look at it for the patterns we're looking for. I'm looking for any def that produces a syntax node, and I'm going to change it. I'm going to wrap it in position node. So I really, with my automation, I really try to just automate what I do, because it makes it easy to read and it makes it easier to write. And it's like not super abstract, but however I think about it, that's how I want to express it. And so this is another compromise way in between regular expressions and writing a full parser to identify pieces of the file that we want to change them. Oh, and this library is entirely TypeScript, so it's just an NPM module, and you can parse this way in any JavaScript program. So this is totally not tied to Rug. It's basically a better regular expressions that other humans can read. Microgrammar. It's in between regular expressions and ANTLR. Okay, so that's the explanation of how we get from an Elm file to understanding it and then to being able to modify it. And the framework also lets me modify it in GitHub with pull requests if I have Atomist in my Slack channel. This is my podcast, Greater Than Code. I've got to give it a plug, in which we talk to people who code or are related to code about things that are more important to code, typically, more important than code. And I'm really excited to be at Atomist doing development automation. Yeah, these are the repos related to this presentation. But what I want to leave you with is just the idea of we can be a wizard without making our code clever, because nobody in my team has to know that I even ran these rugs, and I don't care whether you automate the code that automates code. I hope you're inspired to automate your whatever you do that is multiple steps and combine that into one, because this is how we advance as humans. by adding new primitives to our action vocabulary. Because take deployment automation. If deployment was 7 steps and you make it 1, that's 6 other things that you can think about while you're deploying. And you might think about, oh, what else might affect this deploy? And you might think about, oh, what should I be monitoring? And you might think about, how will I know when this is successful? And you might think about, maybe I should put myself on the pager tonight. And when you do that, when you automate your own work, it's totally different than the software we ship. The software we ship has to work 100% or close to it for everybody on every computer. Your automation only has to work for you. 80% is 80%, and that just saved you 80% of the work. That doesn't work for our customers, the people that we're paid to write software for. 80% gets in their way when they run into something. But when it's your automation, you can fix it, you can do what you want. And I hope you're inspired to at least think about code that modifies code, and also making your own work better. What time is it? I don't know. Okay, I've got one word for you. Since I don't know how late it is, it must not be too late. This whole development automation thing excites me. The other day, I was reading Journal of Organizational Psychology, and I came across a word that I think we're lacking in our industry, and we could use it. The word is generativity. I pulled this definition out of an article about executive teams. Executive teams, like developers, are system builders. They're building systems of people, and we're building systems of code, but we're part of that system. So there's a lot of commonality. Generativity means the difference in your team's output without you versus with you. So if your team collectively produces more because you're there, that's your generativity, as opposed to individual productivity. It's not just what you personally got done off your task list. It's about what you enabled everyone else to do. So when you spend time automating your deploy or encapsulating some knowledge and sharing it with your team in ways that they can all improve, you're generative. And good managers who want good teams are looking for this, not productivity. Productivity may or may not. I know a lot of people who are extremely productive and negative generativity. They actually hold the rest of the team back by making themselves look good. So if you need an excuse to spend some time on automation, there's your word. And thank you for your attention. And I'll be up here for questions, and there's some stickers if you want to stick with.
Questions?
Yes.
So, for a particular
go ahead.
Particular considerations as to not modify the AST and then generate the code, regenerate the code, or yeah.
So I'm technically not operating on positioned node. They don't have an update method. After Rug gets those positioned nodes back, it transforms them into updatable tree nodes, they're called, which in fact do not have their position, they only have their values. But it has filled them in. It's put like fillers in for all the white space. So at that point, the nodes really are, you can read the tree and get the entire file back. That way, when you update it, it doesn't matter that you're pushing everything afterward. And also, there's also the part where after I update a particular node, really all the nodes under it are invalid anymore, and all the nodes above it get a commit message and need to know that they've changed. And so there are places where, like especially my Elm parsers, if I change the update function and then I might want to change that again, I need to reparse the file. So I will. I'll do that update and I'll be like, okay, reparse with the new contents and get a new tree back before I modify that. So thank you.
Thank you. No more questions?
what do you do on syntax that's invalid?
Say it again.
What do you do when syntax is invalid? For example, you have a bad source file.
Oh, when syntax, what do I do when syntax is invalid? So that's a good question. I fail. Like if you haven't run Elm format, the parser will fail, typically, depending on what it is. Now, yeah, I was talking to like Mods Targerson the other day, and one of the things that's fascinating about like Visual Studio and IntelliJ is they have to parse invalid syntax too in order to give you information. I am not your compiler. Use the compiler to find your invalid syntax and then run it through Rug. So, I mean, I'm limiting the scope of what I support to valid Elm. It doesn't have to like symbol check. I don't care about your symbol checks, but it has to be syntactically valid Elm formatted Elm. So this is an example of I'm deliberately limiting the scope of my automation work because I'm not Visual Studio.
Okay, and then that brings me to the second question. When you execute a rug, do you also check if the output valid syntax?
It will fail if the output is invalid, which is kind of unfortunate because it can make it hard to debug the rugs. Oh, I should no, the question was on the microphone. I don't have to repeat it. Okay. Yeah, it will fail if it produces invalid syntax because it won't be able to reparse it again, and that makes it really angry, which makes me sad because I would rather like be able to see it and then know. So I tend to catch exceptions and then print out. Like in my parser, in my real parser, I catch an exception, and if the parse fails, I'll print out what didn't parse so that I can see the updated file and see what I did wrong. Yeah, so that is totally tricky. Any other questions? Okay, cool. There's stickers, so, and they're kind of cute. They're not as blingy as this one. They look more like this one. Thank you, everyone.
Let's have another round of applause.